Hello, I'm Leo Puyo, and in this presentation, in this video, I will talk about this directional blood flow contrast that we've recently introduced in laser Doppler holography and how we can use it to image retinal blood flow reversal. This work has not been published yet. It's being reviewed, but it's currently available on arXiv. So this is what normal blood flow looks like in arteries and vein in the retina, and what we are interested in most of the time is the arterial blood flow profile, and you can see here that it rapidly increases during systole and then it slowly decreases until the end of diastole. One day we encountered this sort of arterial waveform profile in a disease eye. It was affected by both glaucoma and central retinal vein occlusions, and it was very surprising because it rapidly increases during systole, but then it rapidly decreases, falls down to zero, and then increases until the end of diastole, which was very unusual. So we suspected that this was a case of blood flow reversals, but we could not really prove it. So to prove it, we looked around at what was being done in Doppler ultrasound, and we were very inspired by some tools that they have. So the first one that we were interested in was this red-blue directional contrast that they use to identify the flow that is going upward and downward. So this is the ocular globe, and you can see here the central retinal vessels that are identified with this contrast, and transducer would be laid on the closed eye here. So the upward flow is the flow going in the direction of the transducer, and the blue flow is going away from the transducer. Now the second thing that is really helpful in Doppler ultrasound is the use of spectrograms, because it is what really allows to make quantitative velocity measurements in absolute units. So it's in this rectangle here, you can see that the velocity can be estimated in centimeters per second. All right, so the limitation for ophthalmology of Doppler ultrasound is that the spatial resolution is very limited. Here you cannot make the distinction between the arterial and venous flow. So it's assumed that the upward positive flow is the arterial flow and the downward flow is the venous flow. But what happens then in the case of blood flow reversal? All right. So this presentation is organized the following way. I will first talk about the directional contrast that we've introduced in LDH, then the spectrograms that we also use, and how we can use these two tools to reveal blood flow reversals with laser Doppler holography. So starting with the directional contrast that is in Doppler ultrasound here, and here is with laser Doppler holography that we will come to. So to explain how we can have directional contrast, I need to go back to the basics of laser Doppler. So here is red cells flowing through blood vessels, let's say in the eye fundus, and we illuminate it with a single frequency laser diode. And thanks to the Doppler frequency shift, the frequency of the light, the waves scattered by the red cells, is going to be shifted by a quantity that depends on the scattering direction and the velocity vector. So a greater velocity means a greater Doppler frequency shift. Now if there's many scattering, direction, velocity, and especially multiple scattering on the vessel walls, for example, then what you get in the end is no longer a single Doppler frequency shift, but a whole Doppler broadening. And we can study this Doppler broadening to retrieve information about the velocity. So the signal processing in laser Doppler holography aims at doing just that. So we start with the raw interferograms that come out of the camera and that are real valued. We apply a numerical propagation, so it's an angular spectrum propagation, and we end up with reconstructed holograms that are complex valued. On this complex valued stack of holograms, we slide a short-time window, and for each of these windows, we calculate the power spectrum density from the squared magnitude of the Fourier transform, and we integrate only the highest frequency to reveal blood flow. So the idea is that if there's faster blood flow, then there is more energy at high frequencies and power Doppler is greater. And if we do that pixel by pixel, then we're able to reconstruct a blood flow image. To do that, we need to sample the fluctuations at very high speed at 70 kilohertz or so to sample Doppler frequency shift of a few tens of kilohertz. And we can do this with an ultra-fast camera with a frame rate of 500 by 500 pixels. Now, the novelty in this presentation is that there is a sign to the Doppler frequency shift. It can be either positive or negative. So, in the case of direct backscattering, the formula, which is like this originally, can be simplified like this. It's proportional to the wave vector and velocity, but mostly to this, it's related to this angle here. So, in case of in-plane blood flow, then this angle gives a scalar product that is worth 0, so there is no frequency shift. But if the flow is going downward, then this cosinus of the angle is negative, and the Doppler frequency shift is negative. So the frequency of the light that is scattered by the red cells will be lower than the initial frequency. And it's the opposite for upward blood flow. The frequency shift is positive, so the frequency is increased. Now, then it's possible to detect the direction of blood flow if we know the sign of the frequency. It's not so simple, because with the conventional laser Doppler instrument, the signal that you would measure is real, so that the Fourier transform is symmetrical. It's a mathematical law, and positive and negative frequency shift, they cannot be differentiated. But with laser Doppler holography, as you're doing your Fourier transform on complex valued holograms, because of the numerical propagations, you have an asymmetrical Fourier transform, which means that you can make the distinction between positive and negative frequency shift. So in theory, you can do this measurement. Okay, so if we consider an example here, a power Doppler image where we take two regions of interest, where, well, we will show further that the geometry is inverted in these two regions. In the first region, you see that the energy is shifted towards the negative frequencies, and it's actually because the flow is going downward. And in the second region, the energy is shifted towards the positive frequency because the flow is upward. So it means that the energy of the spectrum is actually locally shifted towards either positive or negative frequencies. So what we can do with that is make power Doppler images for each side of the spectrum. So for example, for positive frequency, we can make a power Doppler image, and it's going to be related to upward blood flow. We can also do the same for the power Doppler of negative frequencies, and it results in an image, a blood flow image, that is related to downward blood flow. Now, usually what we depict is the summation of the two halves of the spectrum, which result in an image that is not sensitive to the flow direction. And now what we introduce is an image that is the difference of the two halves of the spectrum. So it's an image that is now sensitive to the flow directions. And it would be very interesting to combine these two information, as this one is not sensitive, but this one, it's black, so it's negative where flow is going downward, and white positive where the flow is going upward. So how can we combine these two images? A very simple way to do it is a basic composite image in a green magenta color composition. But the colors are not really satisfying because they don't match what is currently used in Doppler ultrasound. We want some red-blue contrast. So to obtain this red-blue contrast, we looked at, we design a Hue-Saturation-Value composition. We take the power Doppler difference. this image, we binarize it, so where it's positive, it's red, it means that the flow is going upward, and where it's negative, it means that the energy is more on the negative side, and flow is going downwards, and it's blue. We take the absolute value of this image, and we use that for the Hue matrix, the saturation matrix, sorry, and we also use the power Doppler sum as the value matrix. So in the end, the HSV compositions amount to this, and it should be interpreted the following way, where there is no power Doppler difference and the two halves of the spectrum are the same. The saturation is worth 0, so it means that the image will remain grayish. So the blood flow is in plane. But where there is a large asymmetry of the spectrum, then the saturation matrix has a high value, so the color is very vivid, and you can see either red or blue depending on which side of the spectrum the energy is on. So it's really, this directional blood flow image is the usual blood flow image where you have areas where there is a strong inclination of flow that is depicted in either red or blue, depending on which side of the spectrum. Now let's look at some examples in clinical cases. What I want to show in this first few examples is that you can really well spot the central retinal artery and vein. So in the optic nerve net, luckily all the retinal vessels are more or less vertically oriented, so they give a strong axial directional contrast. So you can really well spot the central retinal vein in blue and the artery in red. You can also very well spot the cilioretinal artery thanks to this red contrast here, and you can see it in all these examples here. So what you see here, it's really the entrance and exit points of blood flow into the retina, and we can spot them because of their vertical orientation. Other interesting examples are cases of venous occlusions where you have collateral vessels that are formed to evacuate the flow that should be evacuated by the occluded veins. And in these vessels you see many red and blue spots, meaning that the flow is going upward and downward and upward and downward in these vessels. And in this other example, you can see that the flow tends to be, well, the vessels tend to be sort of designed in a stairway fashion. So it amounts to the axial tortuosity of the vessel. It's really what you can visualize with this directional contrast. And the last series of example is papillary dispersion. So it's the inclination of the retinal vessel and the optic sheath as it comes out into the retina. So in the example on the left, the retina, the central retinal vessels, they are moderately inclined. So you can see the contrast that is given by the central retinal artery that appear in red below the nerve fiber layers. In the second example, you can also see it slightly. And in the third example, the inclination is so pronounced that you cannot even see the red contrast. It means that there is a severe papillary dispersion. And this is now dynamic examples of this blood flow contrast to show that it's also possible to use this contrast over time. So a single short-time window is enough to produce spectral asymmetry that leads to a good enough directional blood flow contrast. So you can see in red the central retinal artery, and in blue the vein, and other areas where the vessels have a particular inclination. Now, what's interesting to note is that first, in these examples, the directional blood flow contrast remains the same either in the artery and the vein. It preserves the same color, which means that the flow is going in the same direction throughout cardiac cycles. A second interesting feature is that this contrast is very pronounced inside the optic nerve head, but outside in the choroidal vessels you cannot see any directional contrast. And we think that this is because of the multiple scattering of choroidal blood flow that occurs in the RPE that sort of ruins the spectral asymmetry on which relies the directional blood flow contrast, because this directional contrast relies on the direct backscattering that preserves the sign of the Doppler frequency shift. And it's no longer the case when there is multiple scattering in the choroid that will ruin the Doppler asymmetry. Okay, so this video is available on the YouTube channel. Now, the second part of this presentation is about spectrograms. So spectrograms are this way of representing the changes of Doppler spectra over time, and they are quantified in centimeters per second instead of frequency by using the equivalent velocity. And we can do the sort of same in laser Doppler holography, except that we just don't know the Doppler angle. Now, this is an example of a spectrogram gradiated in frequency shift in a retinal artery. Now, what's really interesting to notice is that there can be aliasing, just as in Doppler ultrasound. So here the sampling frequency of the camera was about 60 to 70 kilohertz, and you need that to sample frequency shift up to 30-35 kilohertz, but above that there is undersampling and aliasing that occurs, and this aliasing is not good for estimating the average frequency shift. Now in this presentation, spectrograms are representing the following way. There is a graduation in equivalent axial velocity, so it means that we consider that the Doppler angle is just what it is for direct backscattering of a vessel that is vertically oriented. And we use the black and white color map to just match the color codes of Doppler ultrasound, whether it is for the directional contrast or spectrograms. We do this. Alright, so this is the spectrograms that we can get in out-of-plane vessels. So we use our directional contrast to spot the regions where there is a strong inclination of vessels, and we measure the spectrogram in these two regions. So first in the retinal artery, where we expect the flow to be upward, and we look at the spectrogram and we see this. So indeed, the energy is located on the positive side of the spectrum. And now we look in the central retinal vein, and this time flow is going downwards, so frequency shift expected to be negative, and this is indeed what we observe on the spectrograms. And on both these examples, the energy remains on the same side of the spectrum, which means that the flow is unidirectional. It preserves the same direction throughout periodic cycles. Now, if we want to estimate the average velocity, equivalent velocity, we just fold the two halves of the spectrum, we symmetrize it, and we just calculate the statistical mean of this spectrum. And we find something that is close to 5 centimeters per second in both vessels here, although there are larger variations in the retinal artery. Okay, but now there is no compensation of the Doppler angle because we don't know the inclination of the vessel. Let's look at the influence of the Doppler angle. So to do that, we take another example. We apply the directional blood flow contrast to identify two regions of interest. So first, we are going to look in the same vessels at the out-of-plane section, and we see here that the blood flow is upward, and we find a similar spectrogram. So this time there is a little bit of energy on the negative side, which is probably due to multiple scattering. And the fact that most of the energy is on one side. It says that there is a lot of direct backscattering. In the previous example, it was only direct backscattering. So if light has preserved the Doppler frequency shift value that it corresponds to the flow direction, it means that it's backscattering. So next we look at an in-plane section. So we expect blood flow, blood velocity to be the same because it's the same vessels, just that the orientation has changed. Now the Doppler frequency shift, this should be worth 0, so it can only rely on multiple scattering. And in this time, we found as much energy on the positive and negative side of the spectrum, so it can only be multiple scattering that contributes to the spectrogram. And if we look at the symmetrized spectrogram, well, we find some equivalent velocity shift that are pretty much very similar. So it raises the question of how sensitive to the geometry are the velocity measurements that we perform, because it's not the same scattering regime depending on the vessel orientation, which also raises the question of why there is different scattering regimes. I mean, we hypothesize that it might be because of the preferential red cells orientations according to the flow and the anisotropy of the red cells, or it might also be because of the larger volume that is probed in an out-of-plane section, or we don't know. Alright, so now that we've presented the directional contrast and the spectrograms in laser Doppler holography, let's see what we can do with that to image a blood flow reversal. We have a look again at the case of a very particular blood flow that we were presenting initially. And apply the directional blood flow contrast, and we see that in the retinal artery we see a change of color throughout cardiac cycle, which is very unique compared to what we've seen so far, and it clearly really reveals that there is a change of direction, of actual direction of blood flow. That means a blood flow reversal. Now, with a color composite image, we can very well visualize the artery where there is fast flow in red, and the occluded vein where there is slow blood flow, and it appears in cyan. And when we look at the non-directional blood flow profile in these two vessels, we find very slow blood flow in the vein because it's occluded, and in the artery we see something like this, as described previously. There is this systolic wave, and then blood flow increases until the end of diastole. And with the directional blood flow contrast, we've been able to see that during systole the contrast is red, and during diastole the contrast is blue in the artery. And if we now look at in the central retinal artery with a spectrogram representation of the changes of Doppler spectrum, we can very well see that the first wave is going forward, and the second wave here, it's going downward. So, I mean, the systolic wave is anterograde and the diastolic wave is retrograde. So we show this with this video of blood flow on the left, so directional blood flow contrast that changes with the pulsatile changes of blood flow, and here is the spectrogram that changes accordingly. So this video is also on the YouTube channel. Okay, so let's discuss this. The subject eye, it was affected by both high tension glaucoma and central retinal vein occlusions. So we think that this results in a very high vascular resistance, because the increase of intraocular pressure, it decreases the ocular perfusion pressure, so it makes the perfusion more sensitive to the higher vascular resistance that is due to the central retinal vein occlusion. And what happens is that during systole, the blood pressure is elevated and it's easily able to overcome the high vascular resistance, so you have anterograde systolic flow. But then during the cardiac cycles, the blood pressure falls at some point that it's no longer able to defeat the high vascular resistance, so blood flow falls to zero. And then we think that the prior dilation of retinal arterioles now contracts and give back the energy to the flow, and the flow goes backward because there is less resistance. And so the mechanism seems to rely on both high vascular resistance and arteriolar compliance. Now, blood flow reversals, it's commonly observed elsewhere in the body when there is a high vascular resistance like muscle at rest, but in the eye it's not normally observed because the vascular resistance is very low in the choroid and the retina. In the ophthalmic artery, it has been observed in presence of very severe occlusive carotid artery, but in the retina, very rarely. It's been observed with ICG and fluorescein by Michel in the early 2000s, but it's very rare. It may be rare, and it's probably very problematic because the actual blood flow that enters the retina, it must be quite low, so meaning that the retina is probably in ischemia. And the thing is that with a non-directional blood flow instrument, the retrograde flow would be mistaken as a normal blood flow. So it means that the blood flow value might be found normal, and even the resistivity index that is calculated at the value at systole minus diastole normalized by systole, it would be found maybe normal also, despite the resistivity, the actual vascular resistance being very high. So this blood flow reversals can also be identified with from the ICG pulsation. So in the very first moment of the ICG injection, you can see some pulsatile variations of the ICG fluorescence that should not be here. And it means that the fluorescence, the dye, is going forward and then backward in the vasculature. But it's only very visible in the first few seconds. Okay, so in conclusion, we've introduced a directional blood flow contrast that is able to differentiate upward and downward blood flow. We present blood flow velocity measurements in physical units, and we will probably use the directional blood flow contrast to select vessels where we know that there is no inclination, there is no bias introduced by an unknown Doppler angle, so we know that the blood flow velocity only results from the multiple scattering. And we've used these spectrograms in directional contrast to evidence cases of blood flow reversals, and we would like to investigate more this in glaucoma, because the present study was centered on retinal vein occlusions. So that's it, and thanks you for your attention.